Next, we are going to learn the other kind of variants of recursion. There are three additional variants, but I'm going to focus only the other two. Total recursion and binary recursion. For the multiple recursion, I will not explain it, so you can deal by yourself if you have interest on this recursion. Till recursion. What is the meaning by till? Still means 40. So at the end. Yeah. So till recursion occurs when a linearly recursive method makes its recursive call as its last step. As the name till or at the end. So we usually use this one at the last step. The array reversal method is an example. When you learn about the array reversal method, we know that this kind of things, yeah, the reverse array, it is a kind of the last method. Once you swap it, then you can do with the recursion. When we have the tail recursion, actually, yeah, those kind of methods can be easily converted to non-recursive methods. What does it mean? Non-recursive methods. If we use the recursive methods, we have at least two kinds of content. First is the base, and the other is the recursion itself. So at least we have the base and the recursion. So we call this is the recursion. But if it is a non-recursive, then we can just use for loop, or we can use while do in order to do the repetition. Some people say it saves on some resources. Okay. Now let's see. The iterative reverse array or a comma I comma j. Again, we have an array a, and we have the non-negative integer index I and j. So the reversal of the element a starting at index I and ending index j, it will be the output. The condition will be the same. When you have the I and j, now let's check whether I is less than j. If this is true, then swap ai and aj. And then I will be added by 1 and j will be minus by 1. Basically, this is the same. This is the same with the previous method. We use the reverse array. And then we use the A, which is the array, and then I plus 1 and then j minus 1. So the idea is the same. So I plus 1 means we are going to add the index with 1, and in j minus 1 we are going to add we are going to subtract the j index with 1. The result will be the same, but the way to do the method is different. One is using recursive, and if we use this one, it is non-recursive. Okay, this is the example. If use the recursion or the recursive method, def reverse, and then we have the array. We have what is the starting index, what is the ending index. If start is higher than or equal to n, then return the array. And then we will check what is the element at the starting index, what is the element at the ending index, and then we swap it. So the element at the ending index will be the element in the starting index, and the element on the starting index, it will be the element at the ending index. Then we will do again the reverse array, and the index will be added by 1 for the starting index, and the ending will be minus by 1 for this ending. Okay. If we use the non-recursive method, you can specify just the array, what is the array that you are going to use, and then let's assume that we want to swap for all the elements. Then the starting index will be from 0, and then the ending index will be the length of array minus 1. And then we will check. While the start is less than n, we do the swapping. The array at index n will be the elements at the index start, and the element at the index start will be the element at index n. Now start will be added by 1, and n will be minus by 1. Then we will do again this loop. Okay. Yeah, this is the non-recursion method, and this is with recursion. Now my question is, which one is better? Number 1 or number 2? If you look at those operations, both of them, they have O and they will do the operation at least for n time. Okay. But if you look at this one, the start and n. If you look at this start plus 1 n minus 1, we have the 5 element before. This is the element index 0. This is the element index 4. Once we reach the middle index element, then we stop. So it means at least this kind of reverse array, it runs n divided by 2. Okay. N divided by 2. If you look at the O n divided by 2, yes, there is no n divided by 2. It is approximately, okay, you can say it is approximately, we have the log n. Approximately. What about this? This is also the same. We have the condition start is less than n. So start will be added by 1 and n will be minus by 1. When we have 5 elements, yeah, we have 5 elements, so the operation will just do 1, 2, 3. So at least n divided by 2. Then the operation, the number of operation is approximately is O log n. So both of them are the same with the number of operations. But what is the difference? The difference is only how you define the function. So the function is reverse, and then here you just try to call the function again. But here you just use the repetition. Okay. There is another kind of recursion method. We call it binary recursion method. The binary recursion occurs when there are 2 recursive calls for each non-base case. Okay. So there are 2 recursive calls for every non-base case. We look into the power function. In the power function, we have 2 non-base case. First, when the n is odd, and the other when the n is even. Let's take a look on this binary sum. The problem is We want to add all the numbers in an integer array A. We call it, this is a binary sum. We have an array A and then I and N. Both of them are the integers. The output will be the sum of N integers in A starting at index I. So the index can be any numbers I. If we have, for example, this one, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it means the index can be from 0 until 8. It can be any number from 0 until 8. What about the N? N is the number of integers that you want to sum. Let's say I want to start from the index 3 and I want to sum only 5 numbers. Then 1, 2, 3, 4, 5. So I have the binary sum A, which is the array, and then I, let's say I'm going to start from the index 3, and then I'm going to just do the summation of 5 numbers. Then the parameters will be A, comma 3, comma 5, something like this. Now, in order to check all the operations, we can start from the index 0. Okay, we can start from index 0, and then we just try to reach at the last index, or 8, the index number 8. If N equals to 1, then return A I. Means if the number of integers that we want to check is already reached the base case, then let's return the A index I. If the index I start 3, then we will finish at the index 3. If we start with the index 0, then the last index will be A index 0. Now we do with the recursion. We call it, this is binary. So what is binary? There are 2 options. So here we have 2 functions. The first function on the left function, the binary sum, it will be A, comma I, comma N divided by 2. On the other hand, this function will be A, which is the array, and it starts from I plus N divided by 2 until N divided by 2. So it means I'm just going to check the remaining. Now, maybe it is too complicated to understand this one. Let's see based on this diagram. I want to do the summation from the index 0 until index 7. Okay, let me just make it until 7 for this example. Then I will split this one into 2. This is what we call as binary. We split into 2. The splitting will be based on the N divided by 2. Because we have N equals to 1, 2, 3, 4, 5, 6, 7, 8. So there are 8. 8 divided by 2 means 4. So the 4 numbers on the left will be on the left section, and the 4 remaining number on the right will be on the right section. And then again, after we have those number, we split again into 2. And here we split again into 2. Until we have only one number. Okay. Why 1? Because when we decide the base case, the base refers to N equals to 1. when n equals to 1, we want to start with the A index I. So this is the A index I, this is the A index I, this is the A index I, this is the A index I. And then what you do with this one, based on the function here, we do the summation on the left plus the result on the right. So this is the result on the left plus the result on the right. Then if you do like this one, we will do 2 plus 4. Then the result will be here we got 6, 5 plus 7. Then we got the result is 12. And then when we do back to this level, we have 6 plus 12. Then the result here is 18. What about here? Yeah, until we split to the n equals to 1, we have this result is 17 and this result is 26. And then we go up to this level, the result will be 43. And then we comes up into the original level and we can get the result is 61. So that's the way to do with the binary recursion methods. So I give you the code here. I'm not sure if you can. Oh, okay. This is a good website if you want to look the step by step. If you want to look step by step, then you can see the next. When you click next, so you can see where is now the location. Okay. So you can check if you are having a Python code, then you can check how many operations you need to do for your algorithm. So here, yeah, I give you this one example. This is the binary sum. Yeah, you can try later. Now, in some of problems, we can use the recursion, but in some of the problems, we may not be able to use the binary sum or the recursion. I guess you know the Fibonacci. So we learned about Fibonacci before. And the Fibonacci we can define with recursion. Now let's look at the result F0, F1, and Fi. Okay. So we need to define what is the 0, what is 1, and we can specify the 0 is 0 and the index 1 will have a value of 1. So the index, the I index means the index is higher than 1. We will use the formula I minus 1 plus I minus 2. Okay, so we know that if we have like 1 and 1, like this sequence, so the next value will be, this is the I minus 2, this is the I minus 1, and this is the index I. So we will get 1 plus 1, it equals 2. If now it becomes the I, then we will do the I minus 1, and then we will also plus with I minus 2. Then the result will be 3 because we will do the summation of 1 plus 2 and so on. Okay, so we can use the formula like this one. Now, let's try to use the recursive algorithm. If we use the recursive algorithm with the binary Fibonacci, the input will be a non-negative integer k, so any number, at least it is not is higher than or equal to 0. So the output will be the k Fibonacci number. So Fk, if I have the 5. Then I want to get the 5 Fibonacci numbers. If k equals to 1, then returns k. Otherwise, let's do the k minus 1 plus k minus 2. If you look at this algorithm, is it good or bad? In the sense of the formula, this is the same with the formula. So I have the function. I would like to check what is the element at the previous element, or which is I minus 1, and the last second element, which is I minus 2. So the formula is correct. Now, we need to do the analysis. We need to do the analysis. When we do with the recursive calls with the binary fib, this is the binary Fibonacci. So how many operations do they will do for every of k? When k equals to 0, it is only 1. When k equals to 1, it is 1. When k equals to 2, okay, this problem now becomes complex. So we need to check how many operations for n1 and how many operations of n0, and it will be added by 1 because this n2. Then at least there will be 3 operations. What about n3? The n3, now we need to check the number of operations when n2. Okay, n2 plus n1 plus 1, because at least there will be 1 operation. And the n1, we have 1 operation. Then it means we will do at least 5 operations when it is n3. So you can check all those things. Okay. Let's say now we are in the n8, okay, equals to 8. The k equals to 8 means I'm going to check when the n7, so for 7 times, and then n6. So n7, we have 41 operations, and for n6, we have 25 operations, plus its current operation. Then in total, we have 67 operations when we only want to get 8 numbers of Fibonacci. Then it means when the k, when it is 8, we have 67 operation. When it is 7, it is about 41. When it is 6, it is about 25. Then approximately, when the nk, we want to predict the number of operation of nk, it is approximately 2 power of k divided by 2. So it is approximately 2 power of k divided by 2, approximately. Okay. Then if it is like this formula, then we call this is exponential. So the n will be 2 power of n. You still remember the big O when it is 2 power of n? When the number is high, of course, the operation will be very, very huge. So this is not efficient. Okay. When it is not efficient, then this algorithm is not good. If you try to run this algorithm in your computer, then it will be very, very slow. You cannot get the response in the fast time. And yes, using the binary recursion does not guarantee to get a better function. So whenever you design an algorithm, you need to check how long this algorithm will run. What is the peak O? If the peak O is very huge, then you need to change the way to design your algorithm. There can be another kind of uh, algorithm for this Fibonacci. We can apply the linear Fibonacci, for example. When we do the linear Fibonacci means we just do only one. Okay, and then we try to run this. For example, the input is a non-negative integer k. This is the same. But the output will be the Fibonacci fk with fk minus 1. And we use the linear Fibonacci with only one parameter k. Now the k, if k equals to 1, then returns k comma 0. Otherwise, let's return two numbers. The two numbers I comma j means it is the result from the linear Fibonacci k minus 1. And it will return I plus j comma. Maybe if you are having difficulties with this one, let's look at this Python code. We can define the Fibonacci function, and if n equals to 1, let's return 0, 1. So if I have only one number, at least the number that I can print is 0 and 1. Otherwise, let's divide the a and b equals to the Fibonacci n minus 1. The Fibonacci n minus 1 will be, if you want to print the value, whether it is a or b. Now, the a will be a plus b. And then the last number will be the a. So I can say like this one. This is 0 and 1. Now this is the a and this is the b. When we go to this, now it will be the a and it will be the b. And then if you go again, this will be the a and this will be the b. Okay. That's why we will divide a plus b, because this is the new, and then it will be the a when you have the new variable, and so on. So it will be moved forward the sequence. So if you have the 6, then you can do for 6 numbers. So you can check. If you want, you can check. Let's say I'm going to put this one. Then you can visualize this one. And then you can check how many times or how many operations that it will take for this algorithm. So you can see here, if n equals to 1, so this is not true. Then it will go here, a and b equals to fifth n minus 1. Then it will run again and fifth n, and then if it is not, then we will do this one. So it is a kind of recursion or repetition. Every time the condition is not true, we go to else. And then after we finish, we can get the result. Oh, I didn't print. Okay, you can check later. You can edit with the print. When you open the print, what is the result? So why we need to learn recursive? In some cases, the recursive is good, but you can see from the binary recursion in the Fibonacci case, the result is not good or is not efficient. So one of the algorithm that I'm going to show you is about the search function, and this is one of the best applications using the recursive. In the simple search function, let's suppose we want to search number 22. So the common method to search is to start from the index 0 and go to the next index consecutively. So I have the index 0, and then I want to check. Is there any 22? No. Okay, next. Is it 22? No. Let's check next. Is it 22? No. 22? No. No, 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 no. Okay, this is 22. So this is the way to use the search function. We will do one by one, one by one, one by one, until we got the number that we look for, which is 24, 22. Then to find 22, we need at least 10 operations. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in order to get 22. The Python code will be like this one. In order to find the data, or in order to find the number 22, then I will do the for loop from the index 0 until n time. If I equals to n, then return the number. This is the very simple search. But is it possible to make it better? Now we can do with the binary search. What is the binary search? We have the, I mentioned this one. This is the binary search with loop function. And then this is the binary search with recursion. If you take a look on this one, this binary search, we have a list. And then I want to check what are the items that I want to look for. Let's say, I have the list, and then I want to find number 22. So I need to define the low equals to 0, and then I need to define the high, which is length list minus 1. On this one, we have the data, and then we need to check the target, and then we need to check what is the low and what is the high. Okay. Now, why do we need to have the low and high? Why do we need to have the low and high? Now, let's take a look on the example. In the binary search, we will have kind of 3 cases. First, we need to check the middle value. If the target equals to the mid value, then we found the target. If it is not, then let's check. If the target is less than the data and the mid or in the middle value, then let's recur the first half of the sequence. If the target is higher than the data on the mid value, then let's recur on the second half of the sequence. And that's this one. So we assume that this data already in the sorted. Okay, so it is already sorted. Now, I want to find the number 22. Is it 22? So I need to define what is the, I need to define what is the low, what is the high, and what is the mid value. The low means the smallest, and the high means the highest index, and the mid means the middle value. So here, this is the middle, or the index 7, it is the middle value. And we need to check if we want to find 22. If we want to find 22, then 22, is it the same with the middle value? The target equals to the middle value? No. Then we check this one. The target is less than the data on the middle value, 22. Is it less than 14? No. Then we go to this one. The target is higher than the data on the middle value, 22 is higher than 14. Yes. Then it means then we just skip the second half of the sequence. It means we do not care this one. We do not care the left or the first half of the sequence because we know that the value is higher than the middle value. Now we need to define the new low and the new high. The new low is this one. The new low means the mid, the previous mid plus 1. Then we have the same high, and then we need to define where is the middle value. Okay. So this is the middle value, and after we have the middle value, again check, and then check again. The target equals to the data on the mid. So 22, is it the same with 25? No. And then check. The 22 is less than the 25? Yes. Then we recur on the first half of the sequence. Then we just recur on this one. Now, then we will have a new low, and we will have a new high, and then we will have a new mid. Again, we will check. The target equals to the mid, 22 equals to 19? No. And then check. 22 is less than 19? No. And then check. 22 is higher than 19? Yes. Then we recur to the second half. So we do with only this one. Then the low and the mid and the high will be at the same index. Now we are checking which one is correct. So the target equals to the data mid? Yes. Okay, then we have found the target. So overall, using the binary search, we can find the number 22 with only 4 operations. Previously, we do with 10 operations, but now using this binary search, we can approximately about 4. Okay. So it means we have like log function. So we have 16 data. Okay. This is 1, 2, 3, 4, 6, 7, we have until 15, the index until 15. So it means we have 16 data. With the 16 data, okay, with the 16 data, with log base 2, okay, there are several kind of log. So we can have log base 2, we can have log base 10, but using the log base 2, 16, approximately it is 4. And we can say that using the binary search, this algorithm runs log n. Then this is very efficient. You don't need to do until n times. You don't need to do until n times to get your result, but it can be half, or it can be like almost 50%. Then n. So you can see from the code, okay, if the low is less than or equal to high, okay, we need to define the mid and then check whether the number is the same with the mid. If it is already the same, then just reiterate. If it is not, okay, check whether it is the number that you want to check is higher than the mid or not. If it is higher than the mid, then let's set up the high equals to mid minus 1. If it is not, then let's set up the low equals to mid plus 1. Then we'll do the repetition. You can do with loop function. Now let's take a look with the recursion. With the recursion, we have the low and high. So if the low is higher than high, stop. It means we cannot find the number. Else, we will check the mid value. The mid value will be the low plus high divided by 2. So do you know? Dash slash plus 5 slash 2. The result is 1. The result is 2. 5 slash 2. The result is 2.5. Okay. Using this double slash, it means we want to get the integer result from a division. If we use only one, we want to get the real value, which is 2.5. Okay, we want to get the integer result. Why we need to get the integer result? Because we want to find the index. Okay, this is the index of the mid value. So if the target equals to the data on the mid index, then it is true. If it is not, let's check. If the target is less than the data on the mid index, let's do the binary search. The data will be the same. The target will be the same. Now the low is the same, but the high will be mid minus 1. So we will return back to this recursion. Else, we will do the binary search, data, target, mid plus 1, and then the high will be the same. So this is the second half, and this is the first half. So using this one, your algorithm runs O log n. So it's more efficient than the simple first function. Okay, we can see, okay, from the binary search, this binary search run in the log n. Okay. So every time you do the comparison, it will skip only whether it is mid minus 1 or whether it is like mid plus 1. Okay. Yeah, we can yeah, I think this is the formula for comparing how to see the number of operation when the number is in the low, when the number is on the high. Okay. Thus, its recursive calls divide the search region in half. Hence, there can be most log n levels. Okay. So every time we will divide with 2. Divide with 2. So that's why we call it this is half. Okay. We return into half. But if we use the simple search, it will do every element. It will do 1, 2, 3, 4, 5, at least until n time. So we call this is the n time. Okay, let's take a look on the Google Colab. Yeah, this is the recursion on the factorial. And this is the reverse. I think, yeah, I'm just showing you about the code. Yeah, this is the data, and I'm going to reverse the data starting from the index 0 and until the index 16. Then we can get the data already reversed. Yeah. So if you look at the power, yeah, there is a function in the Python. They call it power, POW. So this POW, they have two parameters, base and the exponent. Basically, Python use the recursive function, okay, for the POW, this one. For this POW, they use the recursive function, the same with what we learned on the class. For the efficiency, they distinguish between the numbers. So whether the n is an odd number or an even number. And if you run these things, it is very efficient. Let's say if you want to check this one with the 1000 data, you can see is very, very small in the numbers. If you do with let's say more than 6,000K, oh, okay, this is not using the, we need to define another numbers for this one, because yeah, the n is not enough if you do with the very big numbers. Okay. So later on, when you do with your experiment, you need also to check what number that you are going to use, because in some cases the big number is not available when you try to do some of the algorithms. So this is the, I mentioned power slow. It means this is just the multiplication with repetition, and this big O will be ON. Yeah. This big O will be O log N, because we half the method, or we half the calculation. Yeah, this is another way to do with the power computation for the fast or the efficient algorithm. We use the partial. So we use the partial, it is to half the exponent, and then the result will be the partial multiply the partial. Okay, I give you this one, 5 slash 2, it means we want to get the integer value. So let's suppose I have this data. Yeah, oh, this is the binary sum. You can check, okay, how the binary sum works. Yeah, this is another the binary sum that we learned from the PowerPoint. Okay, you can check, and yeah, this is the bad Fibonacci, and this is the good Fibonacci. Okay. And yeah, this is the last one that I mentioned to you about the linear search. So because the data is too small, you cannot see. And maybe the operation is very small. In this case, I want to see the number 25. So the number 25, maybe it's only 10 operation. With the CPU, I think it is very fast. But when the number of data is very big, let's say if you have 1 million data, of course, it will need some time to get the result. So using the binary search, you will get the O log N, and it is more efficient compared to the linear search. Okay, let's have a break. I will continue after the break.